Okay. So let's look at the license plate problem.
You know, I'm not going to count my answer out yet.
Okay, so what I would do if I were you, I would draw my license plate. 3 letters followed by 2 digits, and no digits can repeat, but the letters can repeat. All right, so how many choices do you have for the first blank?
26.
How about the second one?
26.
And the third one?
26.
Now, how many possibilities here?
10.
And then, there you go. That's your answer, whatever that is, where they're multiplied together, because you are picking a letter and a letter and a letter and a number and a number. And remember, if you're doing this and this and this, you multiply. Just like problem 1, you're picking a jumper and a shirt, so you multiply those options. Robert?
Did you just go down the line and multiply all of them together?
That's what you do. You multiply those together, yeah. How many committees of 5 can be made from a group of 12? That's 12C5, yep. How many ways can I give away a calculator, a pencil, and an eraser? That's P. Because I can decide I'm going to give these 3 prizes, but it depends on calculator, pencil, eraser, calculator, pencil, eraser, right? The order matters. How many different 5-card hands are possible in a standard deck? C. How many 5-card hands contain 3 diamonds and 2 clubs? 5-card hands, 3 diamonds, and 2 clubs. What's that going to look like? 13C3. That's your diamonds. Times 13C2. That is your clubs. That's it. There's 13 diamonds, you're going to choose 3. There's 13 clubs, you're going to choose 2. All right, quickly on the back side. How many 5-card hands contain exactly 2 hearts? Okay, 5-card hand, exactly 2 hearts. That would be what?
13C2.
13C2. There are your 2 hearts, right?
Times
39C3.
39C3. Now, what's this 13 right here? Possible number of hearts, or diamonds, whatever, hearts in this case. And I'm picking 2 of those. What's this number? That is the cards that are not hearts. And you need 3 of those because this is a 5-card hand. I cannot tell you how many times kids will put this down. Because the problem literally says contains 2 hearts. There they are. But you have to remember it's a 5-card hand, so the other 3 have to come in here, even though they aren't mentioned. How many ways can I distribute 4 identical pencils in a class of 20? What? 20C4. They're identical pencils. It does not matter if you're picked first or last, you're going to get the same prize. 20C4. How many ways can a coach selecting a batting order for 9 players? 9 factorial. That's 9 factorial. Kids, that's the same question as saying how many ways can I arrange 9 people in a line? Isn't it? 9 factorial. How many ways can 4 identical reds, 3 different yellows, and 5 identical blue books be arranged on a shelf? All right, now we talked about this yesterday, but we did not do this particular problem. We talked about duplicates. Remember the letters of the words that were repeated? How did we handle things that were identical? We divided by them factorial, right? So let's look at what we've got here. We've got 4 red that are all the same. We've got 3 yellow that are all different. And we've got 5 blue that are all the same. And we're going to put them on a shelf. How many books are there to put on the shelf?
12.
There's 12 books. Just like a word that had 12 letters. We start with 12 factorial. Now, what do we have to do to that 12 factorial? We got to divide it by 4 factorial and 5 factorial. Think about it like this. Think about it as a word. Red, 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 red. 4 identical reds. Now the yellows are all different. So I'm going to put 1, 2, 3. They're all different. And then the blues are all the same. So think of it as a word. How many letters are in that word? 12. But 4 of them are the same and 5 of them are the same. There you go. That's the answer to the question. How many ways can 7 people be arranged in a circle?
6 factorial.
6 factorial. Remember, when you put things in a circle, it's 1 less factorial. How many ways can 3 algebra students and 4 pre-cal students be arranged in a row? Oh, this is a new concept. Because now we're saying the algebra students have to be seated together. Do you see how that's different? We've not done that yet. This is called bundling. We're bundling them together. Okay, so I want you to think about this. We have 3 algebra students and 4 pre-cal students, and these guys have to be seated together. So imagine that you have a string and you tie them together. They can't be separated. So you have this bundle of algebra students, and then you've got these free-floating pre-cal students. These guys can sit anywhere. But these guys are together. How many things are you really arranging then?
4, 5, or 5.
You're really arranging 5 things. The 4 pre-cal kids and your bundle of algebra students. So you start with 5 factorial. You're not arranging 7 things. Normally I would start with 7 factorial, but I'm really not, because these are tied together and they function as a unit. But there's a second piece to it. Because remember when you tied those 3 together, they could be tied together in different ways, right? How many ways could those 3 kids be arranged within their little bundle?
9.
How many ways? 3 kids can be arranged how many ways? 3 factorial. 6. 3 factorial. So where did the 5 come from? The 5 is the 4 pre-cal and the bundle of algebra. So there are 5 things you're arranging. But this bundle itself could be rearranged 3 factorial ways. Think about it. If I said these 3 have to sit together, couldn't they sit together in various ways? That's what's going on here. That's what that is. That's the arrangements of those 3 that are tied together. Now, what if we said the students of each kind have to be together? In other words, all the algebras are together and all the pre-cals are together.
2 factorial.
That would start with 2 factorial. Because really, big picture, what are you doing? You're arranging 2 things, right? But what? That guy could be arranged 3 factorial, and this guy could be arranged 4 factorial. How many ways can the letters of I Love Math be arranged?
8 factorial.
How many letters are there altogether? 9. So we start with 9 factorial. Are there any repeats in there? Nope. So the answer is 9 factorial. And how many ways can first, second, and third place ribbons be awarded to a group of 10 students?
10 P3.
10 P3. How many 5-card hands contain exactly 3 aces?
4 C3 times
4
50
C3. There's your aces, right? There's 4 aces and you're picking 3.
times 50 C2.
Times, who watch it? Not 50.
40.
48.
48 times
C2. Where'd the 48 come from?
52 minus 4.
Those are the cards that aren't aces. Your deck has been split into 2 piles. 4 aces and 48 other things. You need 3 aces and 2 of the other things. Emma?
When we do these problems and put the answers down, do you want us to actually like solve them, get numbers, or do you want us
Okay.
to write that?
On a test, you'll work them all out, but for now, you don't need to. It takes too long. You might want to practice a couple just to make sure you know where the buttons are in the calculator, but you don't have to work them all out. How many ways can 10 people be arranged around a dining room table? 9 factorial. All right, so that's a good recap of what we did yesterday. Today, we're going to talk a little bit about something different, because we're going to be talking about probability, and one of the big probabilities is called binomial probability, and in order to discuss it, we need to understand a little bit about how the binomial theorem works. So, here's what I want you to do. I don't want you to write this down, okay? I don't want you to write this down. I want you to get the message at the end, but you don't need to write this down. Everybody knows that if I raise x plus y to the first power, I get x plus y. This is called a binomial. 2 terms, a binomial to the first power. Okay, if I square it, everybody knows that means FOIL. When you square a binomial, you don't just square the pieces, you FOIL it. So that would be this, right? Everybody knows that. If I cubed it, now that would be x plus y times x plus y times x plus y. And I know, because I've done this so many millions of times in my life, that this is what it would end up being. Okay, again, I'm not asking you to write this down. I'm not going to ask you to reproduce this. I want you to pay attention to what's going on. There's a message in here you got to get. X plus y to the 4th. Now, you're starting to think either Mrs. Ford is a genius, which is not true, or there's some kind of pattern here, because there is absolutely no way she knows this stuff. And you are exactly right. I do not know this stuff. I do not have this memorized. There is a pattern. So what I want us to do right now is figure out what's x plus y to the 6th going to be.
X to the 6.
This is a trick. Okay, so everybody has noticed already that the first term is just going to be x to the 6th.
6x to the 5th.
Plus 6x to the 5th y. Okay, so you're making some observations about x's and y's. The next term, I'm not sure about the coefficient, but tell me about the letters for the next term. What are the letters for the next term going
X to the
to
4th y squared.
be? X to the 4th y squared, and x to the 3rd y to the 3rd, x squared y to the 4th, x y to the 5th, and y to the 6th. So does everybody get that, the letter part? Notice that the x's start with the 6th and go down, and the y's end with the 6th and go down this way. Also notice that within each term, look what the exponents add up to.
6.
Okay? So if I knew the power on x, I could automatically figure out the power on y, because I know they're going to add up to that power. Right? Now, the coefficients. That's a little bit trickier. So I'm going to look at just the coefficients. I'm going to take out the letters and look at just the coefficients. This is a very famous triangle of numbers. These are the coefficients. This triangle of numbers is called Pascal's triangle. Blaise Pascal was one of the great mathematicians, but like most of the great mathematicians, he ran with a rough crowd, and they knew he was really smart, and so they came to him and said, "Hey, Blaise, old pal, help us beat the game." They were what called gamers, they were gamblers, and they wanted him to help them win. So that's kind of where this triangle came from. It didn't come from this. We use it for this. I'm going to show you how it came from probability, gaming. But first, we got to figure out what this next row. Here's the fifth row. I gave you those numbers, 1, 5, 10, 10, 5, 1. I gave you those. You've already figured out there's a 1 and a 6. And I bet on the end there'll be a 6 and a 1. Would you agree with that? It's that middle part that we have a problem with. Anybody see it? Anybody see it? There's a pattern.
15.
Yes.
It's like the 3 and the 3 together is 6.
Bingo. Bingo. Good job, Mr. Allerton. In order to get this 10 right here, these two numbers were added together. In order to get this 6 right here, these two were added together. So to get the number that goes right here, we're going to add those together. So that's a 15. And then we'll have a 20. And then we'll have a 15, and then there's the 6 and the 1. So you can then fill in your numbers. So what you just learned how to do, and you'll practice tonight in your homework, you just expanded a binomial, x plus y to the 6th power. You just expanded it, and it took you like 2 seconds to do. Now, what does that have to do with probability? Well, I'm going to hang on to that thought for just a minute, and I want to do one more problem to make sure you're ready for the homework, and then we'll look at what this has to do with probability, why Pascal even wrote all this stuff down in the first place. All right, so let's find the 4th term of x minus 2y to the 6th. Now, I erased everything, most of it, but would you agree that each term really has 3 components? It has a coefficient, which is coming straight from the triangle. It has a power of x and a power of y. Now, the reason that this one had a power of x and a power of y is because those were the 2 pieces of the binomial. So in each term, you have an x represented and a y represented. Now, I know what you're thinking. This is 40. There's no x down here. Well, there actually is. It's just x to the 0 power. So every term has an x and a y, and then a coefficient from the triangle. So this problem, every term is going to have what? A coefficient, and then an x, and a negative 2y. See, this is a little more complicated problem. It doesn't have a plain y. It has a negative 2y. So the 2 pieces of the binomial are x and negative 2y. So they're going to be represented in every term. And then you have a coefficient. Now, we want the 4th term to the 6th power. So here's your 6th row. What will the coefficient be? 1, 2, 3, 4. The 4th coefficient is going to be 20. Now, if you FOILed all this out, what would be the first power on x? In the very first term, what would be the power on x? 6. So the first term, x would have a 6. What about the second term? 5, and then 4, and then 3. So by the time I get to the fourth term, the power on the x is down to 3. I erased it, but do you remember watching that happen, kids? The first term was x to the 6th, and then it was x to the 5th, x to the 4th, x to the 3rd. I'm just counting. Now, what did we say about these two exponents? They're going to add up to 6. So as soon as I counted and got 3 here, I knew this one was going to be a 3. So I got my 20. I have x cubed, and then I have, watch it here, be careful, what's that? Negative 8y cubed. Remember, you don't have the plain y in this problem. You have a negative 2y, so it has to get cubed. So our answer is negative 160 x cubed y cubed. Let me try one more of those real quick, and we'll do a probability problem. Let's find the third term of 2x minus 3y to the 7th. So instead of multiplying the whole thing out, I want just one term, just like here. Each term is going to have 3 pieces. What are the 3 pieces? Now the coefficient. Then this one's going to have a power of 2x. Power of negative 3y. Yeah, I'm going to figure that out here in a second. She says it's going to be 2x to the 5th. Now, how does she know it's going to be 2x to the 5th? Well, remember, if you FOILed all this out, what would be the first power on your 2x? 7. And then it would go down to 6, and then down to 5. So this is 5, which means this is 2. Remember, the exponents are going to add up to 7. Now, coefficient. Uh-oh. I need the next row of my triangle, don't I? 7th power. I need the 7th row. I don't have it. So 1, 7, 21. So my third coefficient is going to be 21. So I've got 21 times, okay, what's this? 32x to the 5th. What's this? 9y squared. So we're going to take our calculator and we're going to multiply 21 times 32 times 9. I got 6048 x to the 5th y squared. That's my third term. Okay. Now, what does this have to do with probability? Well, let's consider the simplest of binomial games. Binomial games, 2 outcomes. The simplest game is a coin toss. What happens when you toss a coin? You get a head or a tail, right? Binomial, 2 options. You get a head or a tail. If you tossed 1 coin, you would get a head or a tail. That's it. There's no other options. But what if you toss 2 coins? Or tossed your coin twice? What could happen? You could get 2 heads. What else? You could get 2 tails. You could get a head and a tail, or a tail and a head, right? So in other words, there's one way, if you toss coin twice, there's one way to get 2 heads. There's 2 ways to get 1 of each. And there's 1 way to get 2 tails. There's 1 way to get 2 heads, 2 ways to get 1 of each, and 1 way to get 2 tails. 3 tosses. You could get all heads or all tails. What else could happen? You could get 2 heads and a tail. So head, head, tail, head, tail, head, tail, head, head. There are 3 ways to get 2 heads and a tail. Guess what? There are 3 ways to get 2 tails and a head. You see what's happening?
Yeah.
This row in a coin toss problem represents 3 tosses. This is 3 heads. This is 3 tails. This is 2 heads and 1 tail, and 2 tails and 1 head. These are like the exponents, kids. Like y cubed, only it's h cubed. I guess I should be teaching. So, when somebody says, find the probability of exactly 3 heads when 5 coins are tossed, which row of the triangle will we go to? We're doing the experiment 5 times. We're going to the 5th row. So in the 5th row, what do all these numbers represent? Now think about it. You're flipping a coin 5 times. So this would be 5 heads. What would this be? 4 heads and 1 tail. Think of those exponents. X's and Y's. This would be 3 heads and 2 tails. 2 heads and 3 tails. 1 head and 4 tails, and all 5 tails. Everybody okay with that?
Mm-hmm.
Now, we want 3 heads. So this is the number that we want. Just like the problems we just did, there's 3 pieces to this answer. There's a coefficient, there's the heads, and the tails. Now, you've already figured out your coefficient is 10. When you flip a coin, what is the probability of getting a head? Well, 50% or 1/2. So 1/2 is my probability. What about for a tail? 1/2. Now, how many heads do I want? 3. Meaning, how many tails am I going to get since I'm tossing 5 times? Multiply that together, and that is the answer to the question. That's the probability of getting exactly 3 heads. 0.3125. Now we'll see who's been paying attention. Now the first time I roll a die, kids will say, "Oh, Mrs. Ford, that's not binomial." Actually, it is, because in this problem, my goal is to get 2 4s. So what am I shooting for? I'm going to get 2 4s, and then I'm going to get 4 numbers that aren't 4. So here are my options: 4 and not 4. I don't care whether it's a 5 or a 2 or a 1. No, no, no. It's a 4 or it is not a 4. Those are my 2 probabilities. 4, not 4. All right, so there's 3 pieces to this. There's the coefficient, there's the probability of a 4, and the probability of not a 4.
230.
Now, I'm rolling a die. You know what a dice. I'm rolling it. What's the probability I'll get a 4? 1/6. What's the probability I won't get a 4? 5/6. In this particular problem, I want 2 of these, which means I will have 4 of those, because it's 6 rolls. Right? Now I need my coefficient. I'm doing this experiment 6 times, which means I will go to my 6th row. Now what does this number right here represent in terms of this problem? 6 4s. This number right here represents 6 4s.
That's 15.
So this would be 5 4s, 4 4s, 3 4s, 2 4s. That's the number that I want. Multiply all that together, and that is the answer to the question. Looks like about 1/5, at 20%. Okay? See how that works? All right, let me put your assignment on the board because I still don't have it in school. This is in the book again. We're going to talk more about probabilities tomorrow.
Kluger's already had his experience.
What?